can grow stuff here, and you can grow a wide variety of stuff. And a lot of there are a few landscape places in Tahoe. They pretty much just carry stuff that will grow well here.
Yeah.
We
It's like, I
found.
lived like across the street from a couple of nurseries and got really surprised by the variety of
Yeah.
stuff that they have.
Yeah, there's Aspen Hollows and what's the other one? There's another one on Emerald Bay Road. But anyway, we usually go down to Carson because it's kind of more. There's this place it's called the Garden Center, not a very creative name, but got a bunch of extensive plants and it's cheaper. And you got to be careful though because some of the things they carry can grow in a desert environment like Carson, but won't tolerate the harsh winter. All right, can I erase all this stuff?
It's always remarkable if you're at the top of Heavenly and you look like down at the lake and it's so green at the lake and then it's just so barren. It's such a contrast. Yeah.
It is. It's a big contrast, and you know that is the rain shadow effect for you, right? Sierras gobble up all the precipitation. All right. So we can actually rank things and how acidic they are based on what kind of groups they have in terms of electron donating and withdrawing. So if you're electron donating, you're going to be less acidic. Or pH is going to, be higher. If you are electron withdrawing, you're going to be more acidic. Lower pH. Okay. So, rank these in order of increasing acidity, or in other words, decreasing pH. Remember this? Maybe I should have had you memorize this because we use this quite a bit, right? You probably have an inkling of what these things are. So, dichloro, dichloro, dimethyl. Butyric acid's the same, right? So we can do 1, 2, 3, 4. If we look here, right, our R group, that's electron donating. The electron withdrawing are halides. Even though, remember that they were activators, but they were the ones that fell into that kind of weird camp, right, that was in between. So, R group, this dimethyl, right, that's going to be electron, what did I just say?
Like withdrawing. Or the
Donating.
methyl is donating.
It's 50-50.
Yeah.
This one is electron withdrawing, electron withdrawing.
Yeah, I just got them drawing those ones.
Yeah. Now, electron donating, less acidic. So we can say right now that dimethyl butyric acid is going to be the least acidic, right? So now it's like, okay, well, what about these two? They both have the same number of carbons, same number of oxygens, same number of hydrogen, same number of chlorines, right? They're isomers. What's the difference? 2,4 versus 2,3. So that means 1, 2, that means we have a chlorine here and a chlorine here in the 2,3. And then in that 2,4, right, we have one there. So, electron withdrawing is going to be more acidic, and it turns out the closer they are to that carbonyl group, or essentially the closer they are to that carboxylic acid, the more effect it will have, the more likely it will deprotonate. Okay? So the 2,3, well, here it is in my hand, is going to be the most acidic. And the 2,4 is going to be, in the middle. Make sense? Okay. What do we got here? Same thing. Propionic acid or propanoic acid. Propanoic, propanoic. Everything's the same. The only difference is the number of bromines and the position of bromines. Okay? So if you want to write out the structure, you can. You don't really necessarily have to, I don't think. But go ahead and rank those for me. What you think that might be? What do you think? So they all have electron withdrawing. So it just comes down to number and proximity, right? So dibromos are going to be more acidic than just one bromo. So this is going to be least. And then 2,2 is going to be closer than 3,3, right? So most and middle.
What if you had like a 2 bromo and then like a 3,3 or like a 4,4 dibromo? Would it be kind of harder to like look at that qualitatively?
What are you saying? So if we have, instead of this 2,2, if we had a 3,3,4,4.
Or maybe just like 4,4, like 2 farther away versus 1 withdrawn closer.
Gotcha, yeah. So if we had a 2 bromo that's close,
yeah,
versus a
like a 4,4
dibromo,
yeah.
That's a good question, and I don't have a, I don't have a firm answer for you, but I would guess that more bromines would have a stronger effect than just one that's closer. But
Okay.
that's my guess, so don't hold me at that. Right? This one was easy because it was 3, right? If we were looking at, if this was a 2 and we're comparing it to this, I would think that this would definitely win out because it's only 1 carbon removed. Once you get to 4, now it's getting a little bit murky, right? If it was 6, then murky. Further out, a less of an effect it's going to have.
Okay.
At some point, it won't have much of any effect unless the molecule is somehow structured to where it curves down toward each other.
Yeah.
If we threw in a double bond there and made it cis, but that's a good question. But I don't know at what point you start parsing out. Maybe there's some examples in the book that make it really kind of great. I'll look that up.
Okay.
Let you know. Other questions? So let's wrap it up soon here. I want to go over a couple different ways to make carboxylic acids, and then we'll call it a day, and we'll pick up derivatives on Tuesday. Oxidative cleavage, so ozonolysis. We kind of already talked about this with aldehydes and ketones, but you can take an alkyne, and if you take that alkyne and you oxidize it, you can break it apart into two carboxylic acids. Right? Likewise, you can take a primary alcohol and use that to derive carboxylic acid. You can't do a secondary carbon. Secondary carbon, if it was a secondary carbon, it's not going to have a very good leaving group, so that we're not going to promote the oxidation of it. But with the primary, we get away with that. And then oxidation of alkyl benzenes, kind of, similar to some other mechanisms that we've studied. We carve anything off at the benzylic position, okay? And we tack on our carboxylic acid at that benzylic position. Okay. All right. We can also hydrolyze nitriles. So if you remember what a nitrile is, that's things like essentially cyanide, right? C nitrogen triple bond. We can hydrolyze that. We do a substitution essentially, right? We pull off the bromine, put on our nitrile, and then in the presence of an acid and some heat, we can then convert that into the carboxylic acid. So this is an intermediate step to facilitate this. So think about that again in your toolbox, right? If you're given some kind of alkyl halide on a benzene ring and you're asked to create a carboxylic acid, this is one approach that you can do. You can also do Grignard reagents with CO2, and this is essentially what plants do for photosynthesis to make sugar. They take CO2 and they fix it, so carbon dioxide fixation, into sugar. Okay. I don't think that this would be a very good way to, because as you have found, Grignard reagents are hard to prepare and are very stable. Not a very great solution to our ever increasing CO2 problem in the atmosphere, I was thinking, what if they just sprayed the atmosphere with Grignard reagent? What would that do? It's going to carboxylic acids rain down on us. I don't think it's very efficient. This is not an efficient way to make carboxylic acids, but it is possible if you needed to, if that's what you have. Okay. All right, let's put a pin in it there, and we'll meet back on Tuesday. Don't forget, I don't think anyone's done the take home. I haven't checked today, but Also.